A dipole antenna can be made of any length L, but most commonly we will use a overall length of L equal lambda over 2, and this is called a half-wave dipole antenna. And the top figure shows the current distribution for a half-wave dipole antenna, and you can see that the maximum current occurs at the feed point, and we have a zero current at both ends. The bottom figure here is plotting normalized power density in rectangular coordinates on the right-hand side and in polar coordinates on the left-hand side. No, sorry, rectangular coordinates on the left-hand side and polar coordinates on the right-hand side. And one of the reasons that we like half-wave dipole antennas is that the pattern function reduces nicely. So remember that the pattern function for a dipole antenna, for any length dipole antenna, was given as cosine of beta L over 2 cosine of theta minus cosine of beta L over 2 over sine theta. This whole thing gets squared. You'll recall that beta is given as 2 pi over lambda. So I can use that relationship to make substitutions in everywhere beta L over 2 occurs, and that is that beta L over 2 will reduce down to pi over 2. So the pattern function, if we just make the antenna length lambda over 2, we get the pattern function will reduce to cosine of pi over 2 cosine of theta minus cosine of pi over 2 all over sine of theta. So our squared term here, that means that term is going to drop out, and the pattern function for a half-wave dipole antenna is therefore equal to cosine squared of pi over 2 cosine theta divided by sine squared of theta. So a very nice pattern, simpler pattern function. The radiated power density is therefore given by (15 I0 squared over pi r squared), and then we just need to multiply that by the pattern function. So cosine squared of pi over 2 cosine of theta over sine squared theta. Total radiated power by a dipole antenna is just going to be, of a half-wave dipole antenna, is just that surface integral that we did before. And I'm not going to do the math here. It turns out that that's 36.6 I0 squared for a half-wave dipole. Radiation resistance is equal to 2 times the radiated power divided by I0 squared, which is just equal to 73 ohms. And Dmax is going to be equal to 1.64, which is equal to 2.15 decibels. The higher radiation resistance of the half-wave dipole as compared to the Hertzian dipole makes it a much more efficient radiator. And additionally, you'll see that there is no frequency dependence in here, and that's a really nice thing about the half-wave dipole, is that the radiation resistance is independent of frequency. It's constant across all frequencies, so it's much easier to construct an impedance matching network for this impedance than it is for the Hertzian dipole. So far, we haven't calculated any sort of reactive component of the antenna impedance. You'll recall that the antenna impedance is typically equal to R dis plus R rad plus J times the reactance of an antenna, and calculating reactance of an antenna is going to depend on the behavior of the E fields and the H fields in the near field region. It's a little bit outside of the scope of this class, but in general, for a half-wave dipole, the Z antenna, assuming that we've got a perfectly efficient antenna and R dis is 0, it's going to be 73 plus J 42.5 ohms. So there's a significant reactive portion to the half-wave dipole. The nice thing is that if we trim the length of the half-wave dipole from down to L divided by lambda is equal to 0.485, so if instead of a half wave we trim it down to about 0.485, it'll cause this reactive portion to go to 0. It will not affect the radiation resistance of the antenna though. So if we just trim the dipole by about 4% in its overall length, we can eliminate this portion and we can have a purely real antenna impedance for the half-wave dipole. It's really nice. So here I have a more detailed view of the radiation patterns for a half-wave dipole. So you can see I've got a half-wave dipole here oriented along this z-axis here. The physical antenna, not the package that you will see it in, but the actual antenna itself, is constructed of conductive elements whose combined length is going to be about a half of wavelength at the intended frequency of operation. And you can see from the antenna pattern that this is a simple antenna. It radiates energy outward in the horizontal direction, which is perpendicular to the orientation of the antenna, right? Radiation pattern is going along the y and the x-axis, not along the z-axis. The pattern shown here is these are formed from perfectly thin dipoles with two infinitesimally thin wires that are oriented vertically along the z-axis. You can kind of see that the resulting 3D pattern looks a lot like a donut or a bagel, with the antenna that sits in the hole of the donut and energy is radiating outwards. You can see that the strongest area of antenna radiation is going to be perpendicular into the antenna in the XY plane, so right along that axis right there. The azimuthal pattern is formed by slicing through the 3D pattern in the horizontal plane, which in this case is the XY plane, just like you would slice through it if this was a bagel that you're going to put some cream cheese on. You'll notice that the azimuthal plane pattern is non-directional, and that means that the antenna is radiating equally in all directions in the azimuth plane. So the azimuth plane, therefore, its plane pattern is a circle passing through the peak gain at all angles, which we're showing here in figure C. You'll notice that the patterns in any orthogonal plane are directional in nature, so that the antenna meets the definition of what we would call an omnidirectional. It's directional in one plane, it's not directional in the other. The elevation plane pattern is formed by slicing through the ZX plane in this case, or the YZ plane. Either one would work. And from the elevation plane pattern, we see that the dipole antenna has an elevation plane beam width that is about, the 3 dB beam width is about 78 degrees, as indicated by these two blue lines right here. So if we go down to the minus 3 dB points on both of those, that's about 78 degrees. These lines are drawn, again, where the gain is kind of like down to the minus 3 dB point, which is this circle right here. So, and the elevation plane beam, which just remember it's the distance between these 2 points right there. The gain of the half-wave dipole is approximately 2.2 dBi, so as compared to an isotropic emitter, and the value of 2.2 dPi is achieved at the horizon in the elevation plane and everywhere in the azimuthal plane. So here and everywhere here. So you'll note that the azimuth plane pattern is a circle, and it's passing through the gain value of 2.2 dB at all angles. These values are the 3 dB beam width and gain of a theoretical half-wave dipole antenna. And so dipole antennas are often quoted this way, although many of the dipoles in the market don't quite achieve these theoretical numbers. So, given these antenna patterns, you can see that the dipole antenna should be mounted so that it's vertically oriented with respect to the floor or ground. This results in the maximum energy radiating out into the intended coverage area, and the null of them in the middle of the pattern really won't affect us because, if we're doing it indoors, this is going to be pointed towards the ceiling and that'll be pointed towards the floor. So it won't really affect our radiation. So the last thing I'd like to point out is that you've probably seen a lot of half-wave dipole antenna in your life, and here are just some photos of ones that you may be familiar with.